talking about buffers last time, right? So we'll just continue our discussion of the buffers. So why do people want to deal with buffers? Because they maintain a stable pH. Yeah. Depending on the capacity of the buffer, you know, pH can be very stable, or it can be stable for a little bit and then go. And so how do the buffers maintain a stable pH? Well, they neutralize added strong acids and strong bases. And so if we look at an example of a buffer is going to be, we'll look at an HH buffer. HH would just be a Henderson-Hasselbalch buffer. An HH buffer would be something like acetic acid, which is mixed with sodium acetate. In a buffer, we need significant quantities or significant concentrations of both the acid and the base. Otherwise, I mean, if it were all acid and just a tiny bit of base, then, you know, it's pretty much an acid solution, or vice versa. And so if we have this in a beaker, then thing is, we're going to have an acetic acid acetate solution, which is going to be stable. And so here's our acid, here's our base. And so it's an acid and a base in the same mixture. And we can add, if we add acid, like add HCl, then the acetate will neutralize that. And so whatever H plus or whatever hydronium we generate, so HCl will be neutralized by the acetate. Form acetic acid. If we add sodium hydroxide, the sodium hydroxide will react with the acetic acid to form sodium acetate. So it's not completely neutralized because we aren't neutralizing it to pH 7, but when you look at it, you know, this is strong acid, we're substituting a much weaker acid for that. This is strong base, and we have a much weaker base in place of that. And so it's neutralizing the strong, but we're still left with weak.
Okay, so why is there a limit to such a buffer? Like when we added too much hydrochloric acid, why do we kill the buffer?
You kill the buffer by, you know, you only have a certain number of moles of acid in there. And so the thing is, we need this to be excess. Yeah, because when this runs out, then this is a limiting reagent, and that means we have HCl as our excess reagent. If we have HCl as our excess reagent, then it's just an HCl solution, a strong acid solution, or strong acid mixture. And so this would be an example of a strong acid, weak acid mixture. So it's just an acid mixture. We'll talk about strong acid, weak acid mixture in a little bit. All right, so that's how the buffer works, but there's going to be different buffer concepts too that you should know. One is the buffer capacity, and the other is the optimum pH. So let's talk about the optimum pH first. Optimum pH. An optimum pH, you know, is where we have a 50-50 mix acid to base or base to acid. Usually go base to acid. In the Henderson-Hasselbalch, we take the base to acid ratio. And so if we have a 50-50 mix, well, when we have a 50-50 mix, then the pH of the buffer, using the Henderson-Hasselbalch equation, is just the pKa plus the log of the base concentration over the acid concentration. And the base and the acids, these have to be conjugates for this equation to work. If they aren't conjugates, then you have to use simultaneous to solve, the Ka of the acid and the Kb of the base. And so conjugate pairs, and so that means it's a 1-to-1 mixture. And so this comes out to pKa plus the log of 1, which is just 0. And so the pH is equal to pKa. And so the optimum pH of a buffer system is just equal to its pKa. And so we can take a look, because that's when we're going to have a 1-to-1 mixture. And so any weak acid with its conjugate base can act as a buffer. And so we can take a look at some of these just to see what that pH is. So let me just bring up the chart in the book. We'll take, oops, Ron, I didn't want to go here. Mastering Chem, yeah, I actually did want to go here. Text. So we can take a look at some buffer systems here. Actually, do I want to go chapter 16? Probably I should have went to appendix D. Appendix D would have been better. But since I'm here, we'll go here. Okay. So if we have a 1-to-1 mixture of the acid and its conjugate base, let's say 0.100 molar HiO3 with IO3 minus 0.100 molar, 1-to-1 mixture, that buffer would have a pH of 0.80, its pKa value. And so this buffer would be quite acidic. And so this buffer would try to maintain a stable pH of about 0.80. You could add a strong acid. If you add strong acid, it would react with the iodic acid should be fairly strong. That's fairly strong. It would react with the iodate. If you add strong base, it'll react with the iodic acid, right? And so we can see different scenarios here. Let's take a look at, what is this? Ammonia. Well, actually, this is not ammonia. Let's skip that. They're using HN3, which is hydrozoic acid, and azide, but that's not so common. Let's look at benzoic acid. We have benzoic acid and benzoate. So we make a 0.100 molar or 1 molar. 1 molar would be better because it would have higher capacity, right? It's just going to cost more. And so the higher the concentration, the greater the cost. But the thing is, if you buy a buffer solution, you got to worry about the capacity, because let's say somebody sold you 10 to the minus 3 molar, 10 to the minus 3 molar, it's not going to have very good capacity. It's going to have very low capacity. But it'd have the same pH, as long as one of the restrictions of the Henderson-Hasselbalch is the Henderson-Hasselbalch, these concentrations should be fairly significant, that is, fairly high. What do you mean by high? Well, what we mean by high is, let's say I had 10 to the minus 8 molar benzoic acid and 10 to the minus 8 molar sodium benzoate. 10 to the minus 8 molar is extremely dilute, which means that the pH is probably going to be close to, not 4.20, the pH is probably going to be close to 7. You know, the more and more dilute you are, the closer and closer it becomes to pure water, which is pH 7. So all these will go to pH 7 at infinite dilution. But going on here, you know, we could create a buffer of 4.20. And so you see, these are all the optimum pHs here. You know, here, phenol. Phenol is interesting because phenol is actually an alcohol. And so alcohols aren't usually very acidic, but this is back to chapter 16. It has to do with the benzene ring. You know, when you have a benzene ring attached to the alcohol, then all of a sudden this alcohol becomes much more acidic. And so that means that the benzene ring must be an electron withdrawing group or an electron pushing group to make it more acidic. It has to be more electron withdrawing because it's got to make this more polar compared to a normal alcohol. And so benzene rings are electron withdrawer groups, whereas most hydrocarbons, benzene's a hydrocarbon, most hydrocarbons are electron pushers. Okay, this is a little bit about structure. We're going to talk about it more later.
If they're electron pushers, then what would the delta be?
The delta, if they're electron pushers, the delta pluses would be smaller and smaller. And so the more this pushes electron, the smaller this delta plus grows. The more this withdraws electron density, the bigger this delta plus grows and makes it more acidic. And so things that really are big electron withdrawers, for example, if you have you know, sulfur with 3 other oxygens bonded to it, sulfuric acid, then that's a big electron withdrawing group. But this is interesting because this is an alcohol, phenol, which is in organic chemistry, they call the benzene as a substituent of the phenyl group. PHENYL. So this is also known as phenyl alcohol. But anyway, phenol is really acidic compared to a normal alcohol. It's still pretty weak acid because in this case, you can tell which is stronger. Is the acid stronger or the base stronger? You know, here you can easily see, you know, the acid is going to have the Ka, the base is going to have the Kb, and when we look, you know, if we have a 1-to-1 mixture, which one do we produce more of? Hydronium or hydroxide? Hydroxide, because look at the pH. pH is 10. You know, so this tells you the base is more. Over here, the acids are more. Here, it's pretty close. You know, the acid and the base are about the same. pH is around 7.54 here. So anyway, a 1-to-1 mixture of all these will result in buffers of these pHs here. The same thing, you know, well, if we're looking at, can't I scroll this down?
Okay, so about phenol, why would you call phenol an acid if the pKa is about 10? It's pretty contrary.
pKa is 10, and so the Ka for this acid would be 10 to the minus 10, which is more acidic than water. You know, if the pKa were less than 10, then I would worry. You know, if the pKa were less than 10, I would say, I mean, not less than 10, sorry, less than 14. Or, no, I shouldn't say less, greater than 14 pKa, which would mean the Ka would be less than 10 to the minus 14.
Yes.
Then that really, but a 10 is no problem. I mean, we saw pKa of 10 with hydrocyanic acid.
But why wouldn't we consider phenol as a base instead of an acid?
Phenol is not a base at all. This is covalently bond, so you might think that's a hydroxide, but it's not. And then this is not an acceptor. You know, how actually Well, when you go into organic, then you'd see, but in terms of Bronsted, you know, is this gonna be a hydroxide? I mean, not a hydroxide, is this a base, a proton acceptor? Is it gonna be a good proton acceptor?
Benzene, yeah. Got benzene ring.
Benzene is gonna accept a proton? Where would it accept a proton? The thing that's tricky is you got to remember, you know, eventually what you're going to think about are, you know, acid sites and base sites. And so it is possible that phenol acts as a base, you know, here, takes this proton as there. That's possible. But that's when you start doing, remember what we were doing with Lewis acid-base reactions where we're looking at the mechanism? This is drawing these arrows and then rearranging things and see what happens. Well, we see what happens here when we add that we end up with this. Okay, then where do we go from there? You know, and so continue. And to see, you know, where this leads and how this can be stabilized. And then we can figure it out. And so it is possible it acts as a base, but you know, a pKa of 10 is not unusual. Have you looked at the table in Appendix D? Take a look at the table in Appendix D so you can see.
Okay.
And that's important for everybody because everybody should know, you know, what the range is. Did anybody look at the range? Whenever you look at a table, you should look at the maximum and the minimum. And then go from there. Well, anyway, let's take a look at these. Here we have the bases and the conjugate acid. You know, all these bases are the amines here. Aniline, pyridine, hydroxylamine. So we have all these that look like ammonia. And when we look at the pKb's, you know, the pKb's like 474 for ammonia, but you can see, you know, it depends on what you have bonded to ammonia. So for example, if you bond something like a C2H5, which is normal hydrocarbon, a C2H5, is that an electron pushing group or you say electron withdrawing group? More. It's an ethyl group. It's an electron pushing group. And so it lowers the pKb, which means it becomes more basic or less basic? It becomes more basic. You know, the smaller the pKb, the more basic it is. And so that makes sense because, you know, unlike acids, you know, in amines, we're looking at, you know, how much negative charge density. The more negative charge density, the bigger the delta minus, the more basic it is. And so if we got electron pushing groups like ethyl groups on here, you know, electron rich hydrocarbons, that is going to make it more basic. And then more like an OH. Is an OH electron pushing or electron withdrawing group? So hydroxylamine is going to be less basic because that OH is sucking electron density out. So these are the types of patterns that, you know, you would see had we hit that last part of chapter 16, right? Which we skipped for right now. But you know, you see a chart like this. This is kind of weird, C5H5N. C5H5N. This is a pyridine, and pyridine you're thinking, oh, that's a hydrocarbon, so it should be electron pushing, but it's not very acidic. But C5H5N is pyridine is very, very common. This is an aside, anyway. This is when we get back to pyridine has a structure like this. If I eliminate, it's a ring structure, 5-membered, actually, oops, 6-membered ring. 2, 3. I gotta add one more. What's this? Do like this. Be like this. Oops, I need It's like a benzene ring with a nitrogen stuck in there. And so it's a little different, in fact, you know, and the nitrogen's electronic behavior is going to be a little different. This nitrogen is sp2 versus in a normal amine, the nitrogen is sp3. Here. Aniline has a benzene ring attached here. You can see that benzene ring must have an electron pushing effect or electron withdrawing effect. Electron withdrawing effect there. Okay. All right, but anyway, the same thing here. You know, if we're dealing with bases, typically what we do is we use the Henderson-Hasselbalch in terms of pH, right? But what I would have done here, and this might take more time, is, okay, if the pKb is this, that means the pKa of the acid is 14 minus this, right? And so basically the way I would have done these is I would have just used the same equation, the pH equation, and said, okay, if I'm dealing with ammonium, I'm going to figure out the pKa. The pKa is going to be 14 minus 474, which is going to be 9.26. And therefore, a one-to-one mixture of ammonium and ammonia would be 9.26, right, for the pKa. That's the way. Or you could do the Henderson-Hasselbalch with the POH, you know. This would be the POH. And then you got to figure out 14 minus the POH would be the pH. But we can see some other values here. Things that are more basic than ammonia and less basic than ammonia here. All right, but you know, you might, for example, you know, we want a buffer of not 4.20, we want a buffer of 4.00, you know, or we want a buffer of 7.00, not 7.54. And so oftentimes we don't see a pH that we want. Oh, this is kind of nice. This is right at 10. So phenol works nicely, but all these are between the whole numbers. And so we might look, I should have went to Appendix B first, and look for
Acids that have exacts.
yeah, acids that might. Okay? What's going on here? So into my window. Size. Okay.
It's in the appendix. You want to put this? Just put it up on this.
Okay. Well, actually, I must be close here, I hope. Isotopic masses. Actually, maybe I went too far.
It's a T to read.
Oh, here it is. Okay, now we don't have the pKa's, we have the Ka's. But if we have the Ka's, you can figure out the pKa's. The pKa's are going to be the power, and it's going to be, you know, between, this one would be between 5 and 6, right? Because, or 5 and 4, between 5 and 4. Yeah, and so around 5, and so around 5, 7. Oh, this would be right at 7, right? pKa would be 7.00. And so let's say I want to make a buffer that's pH 7.00, right? And so the best would be to find something with an optimum pH of 7.00. So here, this is an optimum pH. So if I take dihydrogen, what's that called? Arsenate. If I take dihydrogen arsenate and then do a 1-to-1 mixture of dihydrogen arsenate with its conjugate base. What's the conjugate base of dihydrogen arsenate? No, monohydrogen arsenate. And so if I do dihydrogen arsenate and monohydrogen arsenate in a 1-to-1 mixture, I'll have a buffer pH 7.00. That's perfect. Except there's one problem. What's the problem with this buffer? I'd like to use it, but there's a significant problem, and that problem is arsenate is fairly toxic, so I don't want to use it. Yeah, that's a problem. Arsenic. And so we're not going to use that. Let's try to find something else that's maybe less toxic. So do you see anything here? Let's say I want a 7.00 buffer like we used in our I don't see anything right at 7 except hydrosulfuric. Let me see, it's sulfuric. Hydrosulfuric is perfect, right? Except there are two major problems with hydrosulfuric acid. Actually, three. Problem number one, H2S smells really bad. It smells like rotten eggs. Okay. Problem number two, H2S is very toxic. The part per billion level, you could die. And then problem number three is H2S isn't very soluble in water. The maximum solubility of H2S in water is only 0.1. And so the highest capacity we can have for H2S would be 0.1 molar. And so H2S is not a good candidate, unfortunately. Although the pH is perfect, the pKa is perfect. Yeah, pKa is perfect. Okay, so we're looking for something common that's not so expensive that would work well. So anything around 7. This would work here. This would be monohydrogen citrate. Monohydrogen citrate with citrate would work. Okay, except citric acid is not terribly stable. Citric acid can be oxidized. It's pretty electron rich, and it can be oxidized in air, so it's not going to last very long. So is there something else? Okay, dihydrogen phosphate. Dihydrogen phosphate, yeah, this is very close, because if this hit 10, if we have 10 times 10 to the minus 8, that's 1 times 10 to the minus 7. And so dihydrogen phosphate is very close, and dihydrogen phosphate is very common, cheap. And so let's make a pH 7 buffer. But how are we going to make a pH 7 buffer? Because this is not pH 7. And so what we do is we just add a little bit more acid to lower the pH, or add a little bit more base to raise the pH. And so what we can do is we can do this. We can adjust the pH by adding a little bit more acid or a little bit more base. And so the pHs are adjustable. If we look at the base to acid ratio, if we increase this, then the pH goes up, right? This will increase the pH. If we decrease this, this will decrease the pH. But we don't want to go too far. And so the pH is adjustable. Yeah. We limit to this. We want to go with a pH equal to the pKa plus or minus 1. we don't want to veer too far away from the pKa, because the farther we veer, you know, the less balanced this buffer becomes. And so when we go with pKa plus or minus 1, what that means is that this. If we go plus 1, then we're going to have a 10 to 1, you know, base to acid ratio. Actually, let's write this up right here, base to acid. If we go minus 1, we're going to have a 1 to 10. And if we're at 0, then it's just a 1 to 1 or 10 to 10. If we go, let's say, well, let's go with pKa plus or minus 2. If I did pKa plus or minus 2, then to get 2 pH units higher than the pKa, what would the base to acid ratio be?
20 to 1.
Not 20 to 1, 100 to 1.
Why?
Because it's to the power of X.
Because it's log term. And so we're doing powers of 10. And so here, it's 100 to 1. Well, can you get 100 molar? Let's say if I made the acid 1 molar, is it possible to make the base 100 molar? No. And so typically what we do is we make the, let's say we made the base 1 molar, that would mean the acid would be 0.00. No, 0.01. Is that tenths, hundredths? 0.01 molar. And so 0.01 molar, is that very concentrated? 0.01 molar. That's extremely dilute. And so what this is, you know, is it's going to be too rich in base and not enough acid, which isn't so great. Or a 1 to 100 ratio. You know, if we went pKa plus or minus 3, then we're looking at 1,000 to 1 or 1 to 1,000. And so this is becoming less and less effective as a base, because a base has to neutralize either added acids or added bases. And so we try to limit it to this. You know, this is getting too extreme, you know, as far as being too heavily biased towards acid or towards base. All right, and so when we look at this, this is dihydrogen phosphate is going to have a pKa of what? And so let's go ahead and calculate that pKa first. And so right now, this example is we want to make a pH 7 buffer. And so we picked the best candidate. The two best, seemingly best candidates were rejected based on their toxicity. But it looks like dihydrogen phosphate is okay. This has a Ka of 6.3 times 10 to the minus 8, which gives us a pKa of 7. Can somebody calculate this? Give me one more digit. 7.200?
Yeah,
All right.
6 after that if you want.
All right, thanks. No, we'll just leave it. 7.20. Okay. And so we could make a buffer anywhere between 6.2 to 8.2. This would be the buffer range. .2 to 8.2, and so 7.00 should be fine. You know, we should be able to make a decent buffer there, and in fact, it's pretty good because it's really close. And so we just need a little bit more acid or a little bit more base.
It's we need a little more acid.
We need a little bit more acid to drop the pH down, so we just got to add a little bit more acid than base, and we should be able to do it. And so the pH that we're after is 7.00. This is going to equal the pKa plus the log of the base. Okay, what is the base in this case? The base is going to be monohydrogen phosphate, and the acid is going to be the dihydrogen phosphate. even though both of these are amphoteric, their mixture is gonna set, their behavior. And so we know both of these will act as acids and bases. And so we have H2PO4 minus and HPO4 2 minus. And then when we ask is, what is the strongest acid? The strongest acid is gonna act as the acid. And the strongest acid is going to be the dihydrogen phosphate. And so we don't have to worry about dihydrogen phosphate acting as a base. It's just going to act as the acid because we have a stronger base. There's no way dihydrogen phosphate would act as a base because the stronger base would attack first. And the stronger base is what? Yeah, and the same thing. Monohydrogen phosphate is also an acid, but there's no way it's going to act as an acid because there's a much stronger acid present. And that much stronger acid present is dihydrogen phosphate. So even though both of these are amphoteric, once we set them in this mixture, they assume just those roles. Dihydrogen phosphate's the acid, monohydrogen phosphate's the base. And that's it. Now, we know what the pKa is. The pKa is 7.20 plus the log. And so what we have to do is we have to figure out what the ratio is. And so what we're going to do is we're going to solve for that ratio. The ratio is going to be the HPO4 2 minus over the H2PO4 minus ratio, which is going to equal 10 to the minus 0.20. It's going to be 7 minus 7.2, 0.2 negative. So what does that come out to? I'm just skipping a couple of steps here. What is it? 0.63. Give me 29? 09? 6309? Okay, so what that means is we need a 0.63 to 1 ratio. And so for every 1 part of acid, we need 0.63 parts of base. Or, let's go with, let's invert this. If you invert this, then we're going to take, for every 1 part of base, we need how many parts of acid?
0.
No, it's going to be greater. Just invert it, invert key. Something. 1.58. 4. Something like that. All right. So, or 1 to 1, or whatever. Anything that is in the same ratio will work. Or whatever else is in this ratio. And so we have a lot of choices. And so probably the easiest thing to do is I'm just going to make this is going to be a little higher in capacity, right? The 1 to 1.58. I just have more moles of acid, more moles of base to neutralize things with.
Okay, where do you get the 1.584?
You just take 0.6, just flip this. Flip this over. Or, that's one way to do it.
Okay, so you take 1.
Okay, and do this. 0.63 over 1.00 is equal to 1.00 over x, and then solve for x.
Okay.
That's how I get it, okay? Oh, 0.20, because I did this. I subtracted 7.20 from both sides, from this and this. And that's where I got it. Okay, any other?
So it's a 1.58 to 1 ratio of that.
Yeah, and so we'll just do acid at 1.00 molar, base at 1.584 molar. That would work. Or if I want to save money, I could do 0.1 molar and 0.158 molar. or save a little bit more money, I could do 0.63 molar and 1 molar. Actually, I don't, or, you know, anything,
Move the decimal.
you know. If somebody tried to sell you a buffer, you know, a pH 7 buffer, and it was 0.001 and 0.00158, then this has very low capacity, right? This can be easily overwhelmed. So we want something with decent capacity. Yeah. We want significant concentrations. But they'll all have the same pH until you get to a very high dilution, in which pH won't be so great.
Is that relatively expensive?
No. You know, the easy way to make buffers like this, there are different ways. We'll look at it. But it's not expensive. This won't be very expensive, especially if you make it yourself. You know, the easy way that people do this is they just take a pH meter in there, you know, and they have the dihydrogen phosphate, and then they just start adding the monohydrogen phosphate until the pH gets to where they want and then stop. That's it. All right, so this should give us a pH of 7.00. And so what we're going to do is we're going to take a look at this. Just see, do buffers work? Let's see. And so I'm going to just take a cup of water, let's say a half a cup of water. How many mils should I put in here of water? 100 mils? We'll put in 100 mils of H2O. And then what we're going to do is we're going to add 1 drop of 6.00 molar HCl. And just see what happens to pH of this.
It's going to be really acidic.
Yeah, because normally the water should be a pH 7.00, right? We know that 6 molar HCl is really acidic, but there's going to be a huge dilution here. In this chapter, we have to do solution dilution. You guys remember the solution dilution equation? That's the first thing we do in all of these chapter 17 problems is the solution dilution. I call it step I rather than step 1 because it's just the initial step that you got to do in order to do this. And so, you know, 1 drop of water is about how many milliliters? So that's about 0.05 milliliters, right, roughly. They're about 20 drops to a mil. And so, whenever we do solution dilution, we got to figure out the final volume. You know, V final is going to be 100.05 milliliters. Although these aren't significant. It's not a huge dilution, but it depends on who you look at, whose perspective you look at it. If you look at it from the water's perspective, it's not. You know, it's just a drop. But when you look at it from HCl's perspective, you start off with 1 drop and you add up what was 20 drops to milliliters, so you're adding 2,000 drops. You know, that's a significant dilution from HCl's perspective. And so in step I, this is it. The initial step is always solution dilution to figure out what are the concentrations that we begin with. And so we look at the HCl, and then the dilution factor is what we always use. The dilution factor is the initial volume, 0.05, over the final volume, 100.05.
4.99 times 10 to the negative 1, 2, 3, 4.
Times 6.00 molar. And it comes out to what? 4.
Oh, sorry, I didn't multiply by 6, but inside the parentheses is 4.99.
Okay.
10 to the negative 1, 2, 3, 4.
Yeah, and so the dilution factor is V initial over V final. Okay, and then this is going to give us what molarity?
2.99 times 10 to the negative 3.
2.99 times 10 to the negative 3?
Yes.
Molar. Okay. Is there anything else in here? No. That's it. And so what we're going to do is we're going to calculate the pH. Should I worry about hydronium? Do you think hydronium is going to add much? I get 10 to the minus 3 molar hydronium. No, the most I'm going to get from Kw will be 10 to the minus
14.
7, 10 to the minus 8. probably a lot less than 10 to the minus 7. And so let's go ahead with the pH. The pH is going to equal 2.52. Give me one more digit. 4. All right, and so in other words, we went from pH 7 to pH 2.5, which is like close to 5 orders of magnitude. So it just became, what, 10,000 times more acidic, the water did. And so that's a huge change in pH, you know, to go from 7 to 2.5. And so we call this unbuffered. You know, this is not a buffered solution. Okay, let's take our new buffer and see how that would handle the same addition. Actually, this I'm going to keep the same. 1 drop of 6.00 molar HCl, which is 0.05 milliliters. Except this is going to be different. This is going to be 100 milliliters of a 1.00 molar. It was H2 PO4 minus and a 1.58 molar HPO4 2 minus. Was that it? Was it 1.58? Okay. And so this is pH 7.0. Now we add 1 drop of 6 molar HCl. And so the same thing, before we do any reactions or anything, we do step I, which is the initial solution dilution step. And so we do the solution dilution. The HCl is going to be the same dilution factor. It's going from 0.05 to 100.05 milliliters. But we also have to dilute the H2PO4. The H2PO4 minus, this is a minimal dilution because we're going from 100, it's going to be a 100 to 100.05 dilution. In other words, is that a very significant dilution? No, because this would be like a 10,000 to 10,005. Just adding 5 parts in 10,000. It's not very significant, but we might as well just go ahead and calculate it because it's going to change a little bit. And so what does the,
I think it was the other way around.
was it the other way around?
Yeah.
Oh, right, we need more acid, don't we? Okay, sorry. 1.58, 1.00. Sorry about that. So this is going to be 1.58 molar, which is going to give us a new concentration. This is what? This is 2.99, 10 to the minus 3. This is going to give us what? 1.57. Can someone calculate this?
Okay.
5792. Okay. Molar. And they've barely changed. About 1.58. But. Okay, and then the monohydrogen phosphate. Okay, now this is where I differ from the way your book does it. Your book is going to use millimoles. Now, millimoles are very convenient to use too. But after a while, doing a lot of these, millimoles are definitely advantageous for a number of problems, but I think for the bulk majority of the problems, it's just easier just to do the solution dilution initially, rather than do the solution dilution at the end. Okay. And so I always do it at the beginning, but you can use millimoles if you like. All right, 100 to 100.05 of 1.00 molar gives us
0.99.
0.9995. Actually, I'm okay. All right. Now we do step 1. Step 1 in chapter 17. Usually pick the biggest K, and it's the same thing. We pick the biggest K, but now in chapter 17 we have more complex mixtures. And so when we pick the biggest K, we take the strongest acid present. It doesn't have to be a strong acid. Strongest acid plus strongest base present. So what is the strongest acid present? HCl. And the strongest base? Monohydrogen phosphate. Okay, HCl plus monohydrogen phosphate is going to give us what? It's going to give us dihydrogen phosphate and Cl minus. Now, this should be the biggest K, but what is the K value for this?
We don't know.
You don't know, but you can estimate it. What would your estimate for the K value for this be? Just qualitative. Give me the qualitative K for this. No. It's very, very large. This is very, very large. Why not just very large? Why not? Because of this. If I take this base plus water, I don't know what the KB for that is. So let's go to this acid. If I take this acid plus water, that's called Ka. And I know this acid plus water, the Ka is very large. Water, is that a very good base? No. Monohydrogen phosphate is a better base. Monohydrogen phosphate we call weak base. And so HCl with a much better base than water, HPO42 minus, is going to be very, very large. Even better than water, right? And so I know that this reaction's got to go to completion. When does it become very, very, very large? When it's a strong base. So HCl plus sodium hydroxide would be very, very, very large. But very, very large is plenty large enough. And so HCl, this is going to be 2 zeros, 0.00299 molar. HPO42 minus is 0.9995 molar. And H2PO4 minus is 1.5792 molar. And chloride, actually, we don't care about chloride because chloride's not going to alter the pH. But you can put it in there. Chloride's 0 right now. And so the change, the limiting reagent, what is it here?
Probably HCl.
The HCl. So the HCl is going to go to 0. We're going to consume all of it. So it's going to be minus 0.00299 molar. Minus this is all 1-to-1 ratio. So 299 molar minus 0.0299 molar.
He's presenting it.
Do you want plus under this?
Oh, plus, yeah, plus. Sorry. And so this is going to come out to what? So this is 1, 2, 3, 4. So 5 minus 9, 18 minus 9 was 6, 18, 9, 7, 5, 9. What is it? 96? 969. 0.9696. Point.
No, you're nice.
I got 0.96.
Okay. And then this is going to be 1.589.
Barely changes it, 1.58199.
1.581,
You know what, use 1.579, sorry, I didn't use 1.58.
59, sorry, 1.59, 1.6,
1.6091.
1.6091, thanks.
0.00299.
Oh, shoot.
That is pretty small.
Yeah. It's 1.58299.
Sorry.
0.99651.
0.99651.
Yeah.
Whoa, 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 whoa.
Okay. This one's going to be 1.58.
Okay.
19.
0.
Right?
Wait,
Nine
are you
one.
putting 2 zeros after that?
1.581.
Wait, are you putting 2 zeros after that?
29.
219.
219.
I didn't get the same thing.
For which one?
Get the 1.58?
What HPL? Wait, 0.9995? 0.9995 minus 0.00299.
No, she's on the first one.
Okay, good.
Okay. Now we look at what's left over, and what we see what's left over is this. We have what's left over is no strong acid, and we have the conjugate pair. And so what we have left over is a Henderson-Hasselbalch buffer. Well, that makes sense because the buffer has to be in excess here. And so in order to figure out the pH, we don't have to set up another ice table. We just use the Henderson-Hasselbalch equation. That is, the pH is equal to pKa plus the log of the base of the acid. And so this is going to be, the pKa is 7.20. Okay, plus the log of the base of the acid. Now the log of the base is going to be 0.99651 over the acid 1.58219, which gives us what? Okay, so you calculated 6.999, which is 7.00 roughly. And so basically we add a drop of the HCl to unbuffered solutions, the pH changes dramatically. The unbuffered solution doesn't have to be water. It could be something like sodium chloride, you know, or anything that has no buffering action there. But here, you know, because of this. Now the higher the capacity, the smaller the change. And we could see that, you know, let's say if I made this 15 molar, I don't know if we can make 15, probably we could, 15.7 molar, and this was 9.9 molar, you know, if I increase the capacity by 10-fold, then the change here is going to be even smaller, right? And the ratio is going to pretty much remain unchanged, and it's probably going to stay 7.00 here. You know? Whereas if I made the capacity smaller, let's say I made this 0.009. If I made this one 0.009 and this one 0.01, you know, then this change is going to have a much more significant impact on the ratio, right? And so the pH would show a more dramatic change. And so the higher the capacity, in other words, the higher the initial concentrations, the less significant the change is. The lower the capacity, that is, the lower the initial concentrations, the greater the impact of the change will be, and we'll see more dramatic pH swings there. Okay, so this is why in the lab I wanted you to get a feel, not by dumping in, but by just adding drop by drop and seeing. Because eventually this buffer will be overwhelmed. I mean, if we keep adding more and more HCl, pretty soon we're going to consume all of this. And so what happens when we overwhelm the capacity of the buffer, what are we left with? And so let's take a look at what would happen if we were to overwhelm. And so rather than adding, let's say, 0.0299, we added significantly more. And so let's go ahead and do that to this buffer solution. So, this is our pH 7.00 buffer. And now I'm going to dump in a whole bunch of HCl. How much HCl should I pour in here? How much 6 molar HCl should I pour in? I added 1 drop. 20 drops? Let's go with 60 drops. No, 60 drops isn't that much. 60 drops is about how many milliliters? 3 milliliters. 3 milliliters to 100. You know what? I'm going to go with, let's add 20 milliliters of, that would probably do it. What do you think? 20 milliliters of 6 molar HCl? We're going to add 20 milliliters. And then we have 100.0 milliliters of the exact same buffer. And so what's the first step that we have to do? Yeah, unfortunately I can't reuse these concentrations because it's going to be solution pollution. So in this case, using millimoles is handier, but I just don't use millimoles much. And so let's go ahead and do that. The final is going to be 120.0 milliliters. And so let's figure out the new concentrations of the HCl, the H2PO4 minus, and the HPO4 2 minus. So the HCl, the dilution factor is a 20.0 to 120.0 dilution of 6.00 molar, which is going to give us a new concentration of what? One molar? Okay. 1.00 molar. All right, then we go down here. This is going to be, what's the dilution factor for the H2PO4 minus? Dilution factor for the H2PO4 minus will be a 100 to 120 dilution. H2PO4 minus was 1.58 molar, is that correct? The acid, yeah, greater. So this is going to give us and then the HPO4 2 minus is the same dilution factor, 100 to 120 dilution, 1.00 molar. Here's where millimoles would have been handy because millimoles wouldn't have changed, but for most of the problems, this is actually, I think, the easier way. What's that?
183 for
HPO4 2 minus?
Yeah, sorry, yeah. I didn't see the other one above it.
0.83?
Yeah, repeating.
0.8383?
8333.
Oh, 8333, okay. And the H 1.316? 66 molar? Okay. All right, so that's our initial step. And then we go to step 1, the strongest acid plus the strongest base. The strongest acid is HCl. Strongest base would be the monohydrogen phosphate. It's going to yield the dihydrogen phosphate plus chloride. So initial, the HCl is 1.00 molar. The HPO4 H2 minus is 0.833 molar. 8333 molar. H2PO4 minus is 1.3166. So here you could see now the limiting reagent's the buffer. And so we've overwhelmed it. Although the acid component is greater, you know, the acid, we haven't overwhelmed the acid. We overwhelmed the base component of this buffer. If we were adding strong base, then this buffer would have survived. Because the strong base would have attacked the acid part, right, in the same amount. So 20 milliliters wouldn't have been enough. We would have had to use more than 20 milliliters of sodium hydroxide. We'd have to use like 30 milliliters of sodium hydroxide, then we would have overwhelmed it.
How are we overwhelming a buffer?
Because
Is it,
Enough concentration.
buffer is the weak base acid mixture here. And pretty soon we're going to consume all that weak base because the limiting reagent here is this. So it's going to be minus 0.8333, and we got excess acid left over. How much excess acid do we have left over? So this is going to be 0.1667.
Yeah.
All right, we'll just round it there. And then over here, this is going to be plus 0.8333. This is going to be 2 actually. 2.149. Okay, do you see we no longer have our buffer because our buffer was this. Now we have 0 parts of base. And then we look at what type of mixture do we have left over. You know, this is, well, we have, strong acid, and then what is H2PO4 minus? That was our acid, right? But now it's our, well, this was acid, but it's amphoteric. Meaning now it's going to be the strongest base present, I think. Well, anyway, the next step is this. The next step is we take the strongest acid and react that with the strongest base present. And so it's always the same, strongest acid plus the strongest base present. Well, the strongest acid present is HCl, but now the strongest base that's going to be present will be H2PO4 minus. And so this is going to give us phosphoric acid and chloride. All right, so let's go ahead and do that. Here I got 0.1667 molar HCl. The dihydrogen phosphate is 2.149 molar, and the phosphoric acid is 0 molar here. That's my initial. Chloride is 0. The change here is going to be complete, and what we say is the strong acids react to completion, because the Ks are always going to be large. As a strong acid reacts to completion, K should be very, very large for this. Means that the HCl is going to go down to 0. This is going to be minus 0.1667 molar, which gives us 1.9823 molar, and this is going to be plus 0.1667 molar. And so this is 0.1667 molar.
the strong guys react away.
Yeah. And this is also 0.1667 molar, but chloride's neutral, so chloride's not going to impact the pH.
Why did HCl react all the way in the first step?
Good question. Oh, because it wasn't one of the reagents, because it was left over.
Why didn't HCl react?
Or so it didn't go away, it didn't react all the way.
Why it didn't react all the way? Because
Limited reagent.
we consume this base. So HCl is going to attack the strongest base. But we ran out of the base. We didn't have enough base because base is a limiting reagent. But HCl still wants to react all the way. So what HCl is going to do is it's going to seek out the next strongest base present. What's the next strongest base present in this mixture? H2PO4 minus. And so, you know, it attacked the best base, but then it's going to attack the next best base. HCl is strong acid. Strong acids react to completion. And so here, now finally HCl is reacted to completion. Right? You know, after I run out of all these bases, the last base that remains will be water. Right? But anyway, we don't have to attack water because it has this, which is a better base than water anyway. And so we look at what's left over. What do we have left over here? H2PO4 minus and H3PO4. A mixture of H2PO4 minus and H3PO4. Does that ring a bell? That is called a
HH buffer.
HH buffer. This is an HH buffer. But it's a different HH buffer than before. How so? Because the buffer we had before was H2PO4 minus as the acid. This buffer has H3PO4 as the acid. And so here, this is going to be the pH is equal to pKa of H3PO4 plus the log. Now the base is different. What was the base is no longer. And the new base is H2PO4 minus. This was the acid divided by H3PO4. And so the pKa of H3PO4 is actually, it's 2.15 plus the log of the H2PO4 minus. H2PO4 minus is 1.9823 over the H3PO4, which is 0.1667. This gives us a pH of what?
The ratio is over 10 though, to the over.
Okay, the ratio's over 10. The ratio's over 10. Will the Henderson-Hasselbalch equation still work? And the answer is yes. The Henderson-Hasselbalch equation works almost to the extremes. This equation works, but is this a very practical buffer? No. And so that's the only thing. So you can use this equation for ratios up to like 1,000 to 1, maybe even 10,000 to 1, depending on the concentrations. But when you start to get to too extreme, because a 10,000 to 1 would mean something like 1 molar to 0.0001 molar. As you keep going more and more extreme, then you have to worry about the one component becoming way too dilute. But here it's fine. This isn't, this isn't what you'd call a, what do you call it? A very useful buffer, because it would be more heavily biased towards neutralizing acids. We don't have much base capacity, that is, we don't have much capacity to neutralize base, although this isn't bad. What is it? 3.225. Thanks. Okay. All right, then we're done. Because KW, we wouldn't worry about KW after this. So we have to get good at recognizing different solutions because, at the end of step 1, we had a mixture, strong acid, weak base, rampant. At the end of step 2, we had this kind of mixture. And so what types of mixtures are you going to see? So maybe we should do an example. Let's do one where we add base. Should we do that? Okay, let's make a pH 4.00 buffer. So let's figure out what acid we'd use for a 4.00 buffer.
Pink.
Do you see one? I'm going to use acetic acid. And so the next one would be a 4.00 buffer. And so we'll just do this pretty quick. We're going to use acetic acid and sodium acetate or acetate, like that.
Why would you use acetic acid?
When we're taking a test, are we gonna choose our own to make our buffers, or are you gonna give us a guideline?
No, you're going to choose your own. Why acetic acid? Because the acetic acid has a pKa 4.74, which is close. So we can bring it down. And acetic acid is common. One way to make this buffer is we can take acetic acid and then add crystals of sodium acetate. That's one way. But there's an alternate way we could make this buffer, which is probably much easier. Well, the alternate way of making this buffer is we could take acetic acid, not add water, and add sodium hydroxide with a pH probe in here. And so what we do is we just do a little titration kind of deal, where we have acetic acid and sodium hydroxide, and we make sure that the sodium hydroxide is the limiting reagent. Because what happens when acetic acid reacts with sodium hydroxide? Well, when it reacts with sodium hydroxide, it's going to form sodium acetate and water. And so what we do is we have the initial here, and then we have the initial here, which we'll call X, we'll call this Y, and then 0 here. And then we'll just make sure that this is the excess reagent and this is the limiting reagent. And therefore, at the end of this, there's 0 molar sodium hydroxide, and then we have, some amount here at the end, and some amount here at the end. And then this ends up being a buffer, an H80 buffer. And so even though that initially this doesn't look like it would make a buffer solution, this makes a buffer solution as long as the sodium hydroxide is limiting. Well, let's figure out what that ratio has got to be in order to have. So why don't you calculate the ratio? Well, since we're running out of time, let me just give you a quick rundown of the types of mixtures that we're going to see here. We talked about the weak acid, weak base mixture, but there are a lot of different types of mixtures we're going to see in chapter 17. Yeah, we're going to have strong acid, weak acid. Strong acid, weak acid, this is just stepwise. Stepwise, you do the biggest Ka going down to the smaller, and then Kw, eventually. So an example of this would be like, let's say we have HCl and acetic acid. Both are acids, both want to donate hydrogens. We're both gonna donate hydrogens to the water, so we're gonna form hydronium. Which one should be the biggest hydronium ion contributor? HCl. The next biggest hydronium ion contributor? Acidic. The next biggest hydronium ion contributor? Water, Kw. And so this is just stepwise, except this would be step 1, this would be step 2, and then you just keep adding the hydroniums as we go along, right? Other strong base with weak base. Strong base with weak base is the same thing. We just do this stepwise. You know, just start off with the biggest KBs and work our way down to KW. Now, this you might just have a mixture outright. They might just say, okay, let's mix HCl with acetic acid. What's the pH? You know? Well, what the pH is, well, the HCl should dominate the pH there. But we could figure out how much hydronium we're going to get from acetic and how much we're going to get from water in addition to that. So the common ion effect is going to limit how much. So we might just have an outright mixture like this, or, you know, after our step 1, we might be left over with this. Okay, then we have to continue on. And so these are the scenarios that we end up with after doing our acid-base reaction. You know, this is a scenario when we did our acid-base reaction, we ended up with a buffer. Did you recognize that? You know? Or, you know, we might have ended up with any number of these scenarios. For example, if this were an excess, and this were the limiting, then all the acid would be consumed, and we have strong base, weak base. That's a strong base, weak base mixture. How do we deal with a strong base, weak base? Well, then the next step would just be stepwise figuring out all the hydroxide ion contributors. You see? And then we have, you know, strong acid, amphoteric. Well, strong acid, amphoteric would be strong acid, weak base, etc. So we got a whole bunch of mixtures, and we'll look at all those scenarios as we go along here, but we're going to recognize the scenarios after we do our initial reaction, which is strongest acid present and strongest base present. Okay, I'll stop here since we're out of time.